In this video, you will learn how to create this interactive 3D animated website hero banner just with HTML, CSS, and JavaScript. No 3D website framework, no GSAP, no external animation libraries. If you want to master modern website animation and level up your web development skills, this video is for you. To prepare for this video, I spent a few hours putting together a modern hero banner using clean HTML and CSS. It looks fine, neat typography, decent web design, but it is completely static and passive, the kind of page you have seen 1,000 times. But watch what happens when we write a few lines of clean CSS and connect the user's cursor directly to our background media. Suddenly, your website behaves like a premium 3D product catalog. As the user moves their mouse horizontally, the background video scrubs smoothly forward and backward, letting them interactively rotate the product in real time. No heavy 3D website frameworks, no GSAP, no bloated third-party animation libraries, just pure native browser APIs. And notice those staggered entrance animations rolling in on load. The glassmorphic panels, the cascading spec pills, the floating annotations. That is all driven by pure hardware-accelerated CSS animation. Zero JavaScript touches any of that. Now, interactive video scrubbing is historically notorious for causing browser stutter, frame drops, and total hardware decoder freezing. Most scroll animation tutorials either use a heavy library or they map absolute coordinates directly to the video timeline, which completely floods and crashes the browser's decoder the moment the user moves their mouse too quickly. We are doing neither today. Instead, we're going to learn the performance engineering principles that keep this running at a locked, buttery smooth 120 frames per second, using lightweight, native vanilla JavaScript. The same principles used in high-end creative website design studios, implemented from scratch in clean, readable code. To keep this tutorial tightly focused, we're exploring the core animation systems, the CSS animation, and the video scrubbing mechanism. If you want a complete line-by-line build tutorial of the entire layout, the grid system, the custom glassmorphic inputs, and mobile fallback layouts, just comment full build below. If we get enough interest, I'll release that walkthrough next week. Now let's open our editors and write some code. We're starting inside our CSS style block. Before we can animate our elements, we need to declare the keyframe blueprints that tell the browser how to translate and fade them. To ensure our animations run smoothly on high refresh rate displays, we are animating only opacity and transform. By avoiding properties like top, left, or margin, we bypass browser reflows and run our animation directly on the graphics card GPU for hardware acceleration. With our blueprints ready, let's apply them to our static HTML components. First, find the background container HeroBG video container. We set its default state to opacity 0 to prevent any ugly page load flashes, and then call our fade-in only keyframe with a tiny 0.1s delay. Next, we do the same for our semantic header and left sidebar. Notice the staggered delay properties. The sidebar begins revealing at 0.5 s's and the header enters right after at 0.8 s's. This establishes our visual loading sequence. Now, let's animate the right-hand side specifications list. We want these pill components to slide in smoothly from the right. But instead of animating them all simultaneously, we want them to enter in a sleek, staggered cascade. Rather than manually writing individual classes for each item, we can write a highly efficient CSS stagger stock using the Nth-Child pseudo-selector. By assigning incremental delays from 1.3s to 1.6s to each consecutive list item, the browser automatically staggers their entry, creating a highly polished premium cascade with just a few lines of CSS. Let's save our CSS, refresh the page, and look at that loading sequence. Beautiful. Now let's move into our script block and make this background video fully interactive. Now, let's write our JavaScript logic. Our first goal is browser performance and memory safety. To calculate how far the mouse moves across the screen, our script needs to know the width of the browser window. Many developers make the mistake of querying window.innerWidth inside their high-frequency mouse event handlers. Asking the browser to calculate layout dimensions inside a function that fires 120 times per second forces a severe rendering bottleneck called layout thrashing. The browser has to stop all rendering to calculate layout widths, causing noticeable stuttering. To prevent this, we cache the window width once on page load inside a variable called cached width. Then we set up a simple resize event listener that only updates cached width when the browser size actually changes. Inside our scrubbing math, we reference this cached variable, making it a zero-cost lookup. Next, we must resolve an elusive HTML5 media race condition. If a video is cached, its metadata loads instantly, often before our script is fully parsed. If that happens, our loaded metadata event listener will never fire, and our duration variables will remain broken. By writing an explicit check for interactive video.readyState greater than or equal to 1, we verify if the metadata is already loaded. If it is, we run our initialization immediately. Otherwise, we fall back to our standard event listener. This ensures our video calculations never break regardless of network caching speeds. With our variables ready, let's write our mouse tracking logic. If we mapped the cursor's absolute coordinate to our video timeline, the video would jump erratically whenever the user moved their mouse quickly. To make it smooth, we use relative delta tracking. Instead of checking where the mouse is, we measure how far it has traveled since its last position. We calculate the difference, the delta, between the current position and our stored prev x. We then convert that tiny distance into a proportional timeline offset. This relative offset is added directly to our target timeline on every frame. This means the video responds organically to the velocity of the user's hand. But this introduces a new physical limit. When the user's cursor reaches the edge of their monitor, their movement stops and the delta drops to 0%. This means they can run out of desk space and get stuck at 80% of the video timeline. To solve this, we use linear interpolation, commonly known as LERP. Instead of forcing the video to snap instantly to our mouse coordinates, we tell it to drift there smoothly. We track two separate values: target time, where the mouse wants the video to be, and current render time, where the video actually is right now. On every frame, we run our LERP easing formula inside a RequestAnimationFrame loop, which syncs our frame updates perfectly with the monitor's native refresh rate. But what happens if the browser is slow and still rendering a frame when we request the next seek? To prevent seek flooding, we implement a seek gate lock. When a seek starts, we set our gate to isSeeking equals true. This blocks all subsequent seek requests until the browser finishes decoding the current frame. Once rendered, the browser fires its native seeked event, which resets the gate to false and lets the next frame through. This simple lock prevents browser stutter and ensures a highly fluid experience, even on older hardware. And just like that, using clean, optimized vanilla JavaScript and lightweight CSS transitions, we have built an immersive, interactive hero section that feels like an expensive 3D website. Buttery smooth. Zero libraries, zero GSAP, pure web development fundamentals taken seriously. Let me recap exactly what you have mastered today. CSS keyframe choreography with staggered entrance loading sequences. Relative delta tracking to map mouse velocity directly to playback time. Linear interpolation to ease video transitions and prevent compression artifacts. The RequestAnimationFrame loop to keep calculations synced with the monitor's refresh rate. The seek gate lock to prevent hardware decoder floods, and viewport dimension caching to completely eliminate layout thrashing. As I mentioned earlier, this full code base has a lot more under the hood, including fluid grid blueprints, responsive mobile fallbacks with a static image swap, a live variables-driven theme switcher, and custom inline inputs. If you want the complete line-by-line build walkthrough from scratch, comment full build below, and if we get enough comments, I will release that video next week. The source code is linked in the description, and if you want my free CSS animation cheat sheet, comment cheat sheet below and I will send it right over to you. Drop a like if this video leveled up your front-end web development skills, subscribe so you don't miss the next project, and I will see you in the next build.